So this is where I left you, and I left you with this example problem that was our last one that I said, you should know how to make this, and we get a benzene ring with a 3-carbon chain and an OH group on it, and I said that this one was a little different because this really only has one group on it, doesn't it? There's just one group on the benzene ring, and that is it. And then we have to add on a 3-carbon chain. So we have to start with benzene. That's the thing of the question. You have to start here. Okay, well, if we're only going to elongate by 3 carbons, we typically said that we have to do that first, just to be safe. But, there's no other groups on here. There's no other groups. So we're going to go through and elongate the chain because that's really our only option at this point. Well, I can elongate the chain by using Friedel-Crafts. I know that. Okay, well, how do you want to do it? Well, it looks like to me at this point right there, maybe this is an acyl type of reaction. Because if it's not an acyl type of the reaction, then a carbocation will rearrange. And I don't want it to rearrange on me. So you're going to come through and you're going to probably say, hey, we can do a 3-carbon chain and double bond O it. And then we can go through and add on that carbon chain. Okay, well, if that's what you do, how are you going to get the OH group on there? Because look, if this is what happens in the first step, and you get this benzene ring with a carbon, 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 and a double bond O that's here, you might be thinking you're clever, and you might say, well, we'll just protonate it, and we'll put the H right there, and that will give us the OH group. No, that's not going to work, because that's not where the OH group needs to go. It needs to go on the middle carbon, not on the end. So, folks, that step is not going to work for you. If you get to this point right now, how on earth are you going to get an OH group onto the middle carbon? So there is a better way to do this. We still Friedel-Crafts it. We still Friedel-Crafts this thing. But here's the key. Friedel-Crafts is an R with a Cl. An R is a carbon chain. Remember, any old carbon chain. Okay, well, if it gives me a choice to pick whatever I want to go, then why don't we pick this? CH2 double bond CH CH2 with a Cl. Why not that? And then we'll do an AlCl3 like we need. And if that goes on, well, let's think about what goes on to that spot. That chlorine leaves. Carbocation forms. Well, Tracy, you just told us that carbocation rearrangement happens, and it looks like the carbocation will Well, wait a minute. It doesn't rearrange, does it? It doesn't rearrange. So, why not? Why does this not rearrange on me like the other one did? Folks, it's because this carbon, when it forms a carbocation, is the allyl carbocation. That was a Chemistry 251 topic because we talked about allylic and vinylic carbocations. This has formed an allylic carbocation. If it shifts left-handed, that is a vinylic carbocation. And we've already talked about the problems, a no-no with vinylics. And that's because a double bond is right beside of that positive charge, meaning that that carbon holds a negative on one hand and a positive on the other. That's not very stable. The molecule's going to hate that. And because of this setup, my allylic carbocation is more stable. Therefore, my allylic carbocation stays at that position. And that also means that this group is the group that goes on to the benzene at this point. All right, so there's step number one. The key step is to realize that if this is what I pick, Carbocation does not rearrange, and that's good because I don't want it to. It just so happened to work out that way. And then the next key step is to realize that this R group can be anything it pretty much wants to be, and Friedel-Crafts acylation is okay with that double bond being present away from that chlorine. Now, this is the group that I have it added on. Now, you're looking at this group and you're thinking, oh, well, that kind of makes sense now. What I have here is a double bond, and that double bond is going to react with something like water and acid. I mean, this was like a chemistry 251 reaction when we talked about the reactions of alkenes. There were tons of reactions with alkenes back in the day. Water and acid was one of them. So what that means is that I'm going to take this benzene ring and I'm going to go through and CH2, CH double bond, CH2. The double bond's going to break. There we go. You remember that noise if you've had me for Chem 251. Hydrogen goes on to 1, so bink, hydrogen plays with other hydrogens because they're snooty. Ew, there they go. And then the OH group is going to be added on. So a carbocation is formed there, and an OH group gets added on here, and we've got it, right? No, 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 no. The carbocation, before it takes the OH group, will shift. Huh? What do you mean it shifts? Okay, well, right now, the location of this carbocation is secondary. Bing! If it goes there, that is a benzylic carbocation. And we talked in Chemistry 251 that a benzylic carbocation is more stable. That benzylic carbocation will accept that positive charge, and that is before the OH group comes. And if that's where the positive charge goes, that is not going to give me my product that I'm after up here. That OH is going to go on the benzylic carbon and not the carbon next to it. So water and acid's not going to work. It's not going to be your friend this time. And that's because this crazy carbocation will shift to the carbon next door. All right, so I'm going to have to go back up here and I'm going to have to erase that. That's such a Debbie Downer moment. All right, so I'm going to go back to this. CH2, double bond. I need to figure out, okay, well, maybe if we, like, anti-Makovnikov it. Do you remember those anti-Marky Mark reactions? Okay, well, anti-Marky Mark said that I could do things with, like, BH3 and THF, and then I can go through and add a round of peroxide and water and OH groups. Okay, well, if that's what you want to do, the double bond breaks. There we go. Hydrogens do not play with other hydrogens this time. Hydrogens will go here instead. And then this spot will get the OH group. That's what an anti-Makovnikov would do. That's not going to work out either. That's so sad. So my borane and THF addition that we learned back in Chemistry 251, I hope, and the acid-water addition that we learned back in the day, even the mercury round. You know, there were multiple ways that we talked about adding an OH group on. Even the mercury round will not work. And that's because it goes on in a traditional type of environment. So how on earth can we get this OH group onto that middle carbon? That's the trick with this problem. Well, there's another way that we can do this, and it was another alkene reaction that we learned at the time. We didn't use it a lot, but it was back there. And the reason they probably introduced this example is to make you go back and pull that reaction up out of the dust. And this reaction was using MCPBA. And what it did This abbreviation was a benzoic acid. Go back and take a look at that. Look it up if you don't remember it. This MCPBA was a reagent that went in and it grabbed both of these carbons involved in the double bond and it made an epoxide. That is what that reagent did. That was its purpose. That was 251 stuff. I mean, that was like lecture 4 or something that we talked about. It was the reactions of alkenes. One of the first lecture modules that we talked about involving reactions. So now that we formed an epoxide, this is great. Because now it locks these two carbons into the bond. And one of those carbons is exactly what I need. Not only that, but look at this. That carbon now is attached to an oxygen that could be part of my OH group that's right up here at the very top. As long as I can break open the epoxide group, then I'll be okay. All right, well, how do we break open the epoxide group? Okay, well, there's a couple of ways to do this. And the route that we're going to choose here is NaH with maybe some hydrochloric acid in the end. So we'll have a benzene ring. Carbon, carbon, carbon. The epoxide is there. The NaH, well, that's going to go in. Bing! Open the epoxide group. That epoxide group will now turn into a H here, and a hydrogen gets added on there to complete the number of bonds that that carbon needs. Folks, a couple of ways to open up an epoxide. You got to be careful, though, because when we talked about epoxides, they can either open up to the left-hand side or they can open up on the right-hand side. We need this epoxide to open up on the right-hand side. So that was the whole deal with the epoxides back in the day. All right, now let's go back and take a look at the other four. D, E, F, and G. D, E, F, and G, I do not want you to worry with. I'm not going to ask you to go through and answer these types of problems. They are involving reagents and reactions that we haven't yet talked about in order to make these the proper way. So it's going to be very difficult for you to use what you know at this point. I'm not going to slam you with extra things that we need to go through and use in order for this to go forward. So because of that, I'm going to say, let's just not do them. So A, B, C, H, and I, that was our focus there. So the next section of the lecture material is tri-substituted. Oh no, tri-substituted. So I torture you with benzene, and then I torture you with benzene with one group. Then I torture you with benzene and two groups. And now I'm going to torture you with benzene and 3 groups. All right, so here's the thing. What you see on your screen right now is a benzene, and this benzene has an NO2 group and it has a CH3 group. The NO2 group, we've already said, was a deactivator, and this is a meta-director. Okay, so meta to the nitro group, that's what that means. So ortho meta. So it would take it here and it would also take it there. Now let's take a look at the methyl group. This methyl group is a activator. And that activator is a ortho and para. All right, well, if it goes para, no. Here we go. There's already something at para. Can't direct anything there. So the methyl piece, the OP director piece, can't direct it to para because something's already there. So the only thing it can do is also do ortho, and ortho just so happens to be right there. So look at this. A magic little marriage came together, and both of these groups are targeting those two areas right there, which would pretty much be the same. So if we add on a third wheel, and this is an NO2 group, because this is a nitric sulfuric acid step. If we're adding on an NO2 group to this, folks, that's great news, because the NO2 is going to be directed to go ortho from the methyl, and it's also going to be directed to go meta from the nitro, and that just so happens to label each one of these. And it doesn't really matter which side nitro goes on, but there is my third group on the benzene ring. So these reactions are very similar. It's everything that we've talked about plus one more. And that one more is just to understand that there are two competing groups on a ring. And those two competing groups are going to try to outdo each other. It's like neighbors competing with the Joneses. They're going to try to outdo each other until one of them has their way. And in this case, the neighbors work together. And they both told the incoming group where to go, which was the same spot. So NO2 had no problem. We just so happened to draw it on the right-hand side. We could have drawn it on the left-hand side there as well. Now here's another example. This example is a benzene with a methyl and chloro. Okay, well, no difference here. The chloro, though, is a deactivator. It's a weak deactivator, but it's a OP director. All right, so OP, so there's the para for that one. And then the ortho would be here, and the ortho would be there. All right, so those are the three spots that the chlorine would be directing an incoming group. That incoming group, yet again, is a nitro group. They're keeping it the same. All right, now let's take a look at the methyl. The methyl group's up here. This methyl group is an activator. That activator is an OP. All right, so with that said, the ortho is there, and the ortho is there, and the para is directly across from that methyl group. Folks, it just so happens to be the same groups all over again. No difference in the first example that we did. So I have this ring. This ring has three locations that are available. These three locations are available to the NO2 group when it gets added on. And we do see a mix, but not a mix of all three. And the reason here is because we've mentioned this before, but this methyl group takes up space. This chlorine takes up space. This nitro group that comes in, right in here is really tight. I mean, this is like a huge mansion and a huge mansion and a little bitty plot of land in between the two for you to build a house on. There's no way. You don't have enough room in there. So the NO2 is not going to want to go into that spot, even though it's available, even though it's directed to go there by both of these groups. It's not going to want to go there because it has a really hard time getting in there in the first place. So because of that, we see an NO2 group that's attached to the left in the ortho spot to the methyl group. And we also see an NO2 group down here at the bottom, which is ortho to the chloro, but para from the methyl group. So we do get a mix. Those are our two possibilities right there. But we do not get the third because of the steric hindrance that's at play. Finally, let's take a look at another one. Maybe not finally, but kind of our last lecture type of topic. Here we see a benzene with an OH and a CH3. All right, so the OH group, let's talk about this one first. This OH group is an activator. The activator is a OP director. All right, so the ortho is going to be here, and the para is directly across from it. It can't work out. Okay, there's something already there. Now let's take a look at the methyl group. The methyl group is also an activator. Not as good, but it's an activator. It's also an ortho para director. Well, it can't go para. There's something already there. That's the OH group. So it can go ortho. So these 4 carbons are all possibilities. What happens now? If these 2 groups disagree, and that's what goes on here, they've disagreed, and all 4 of these carbons become a possibility, which one is going to win out? This is like your mom and your dad, right? Who wears the pants in the family? You go to your dad, they tell you one story. You go to your mom, they'll tell you another story. I mean, you remember that when you were younger? Which one are you going to prefer to go to get your way? So this bromine's going to come in. We got a bromine incoming. And bromine's going to say, hey, I want to go out to the movies tonight. So it's going to figure out which one is it going to get its way with. Which one is going to run the house. Which one's going to put the foot down and say, no, you're going to stay home and do your organic homework. Well, I've got OH and I've got CH3. Both of these are activators. However, the OH is a better activator, and that better activator, because it's stronger, is going to have its way. It's going to set down the rules to the ring and to the home. And that OH group is going to say, bromine, you're going to listen to me. I call the shots around here. You don't. Your mama don't. Or maybe your daddy don't. And that OH group is going to say, I am stronger. I'm going to make the decision. My para is already taken. So you are going to listen to me and go to my ortho positions. So these, those are not choices for that bromine to go to. That OH group is going to make that bromine go ortho, because it's an OP director. Now, they've drawn the structure with the bromine on the left, but you could also do it to the right. It's the same molecule. It doesn't matter. Okay? What about this one? We've got a benzene ring. Here we have a methyl group. That methyl group is an activator, so therefore it's OP. P is taken, so ortho here and ortho there. I have an ethyl group down here at the bottom. Same story. This is an activator. That activator is an OP director. P is taken, so therefore para, and therefore para. I mean ortho and ortho. Again, they disagree. One's telling this incoming group, go here and here. The other one is telling the incoming group, go there and there. Who does nitro listen to? Because that's what we're getting ready to add on to make our tri-substituted benzene. Well, these are equal strength. They both call the shots. And if they're equal strength, because this is an R group and this is an R group, it's the same type of group. On the chart, one does not outweigh the other. We get a mix. Nitro's going to come in. No. Mom, I want to go to the movies. And mom says, okay, but this is what you've got to do. And it goes ortho to the methyl group. And then, no, Mom, Dad, I want to go to the movies. What do you think, Dad? And Dad says, okay, but this is what you've got to do. And nitro goes there. Ortho to the ethyl group. So we get a mix. Both of these form. We can't really control it. That's just the way that it is. So here you have an example of 2 groups on a molecule with competing sites of attachment, and they are unequal as far as strength. Here you have an example of a benzene ring with 2 groups, competing carbons, but the stronger one will outweigh the weaker one every time. And then here and here, you have an example where we have 2 groups, and these groups just so happen to be identifying the same site of location in agreement. So there is no questionable spot of where this thing will end up going. So let's take a look at these example problems. What is the major product for each of the following reactions? So now what they're doing is that they're giving me a benzene with 2 groups on them. They want me to use what we've just learned, and they want me to undergo a reaction with them. And this really will be our last example problem that we'll do in the class, as far as the lecture material is concerned with benzenes. So why don't you take a few minutes before playing the next video, try these. See what you come up with. See if you can determine which one is going to outweigh the other and what kind of product will form because of it. Good luck, and I'll see you in the next video.